Well, first of all, let me just tell you this may turn out to be important to you, but it's not a direct answer to your question. But I have published an autobiography, uh, which is available on Amazon. It's called Confessions of a Jewish Priest. I'm also a priest in the Episcopal Church. And so a lot of that, how I got interested in science and things like that, I talk about that quite a bit. So
Okay.
that's just for reference. I don't mind repeating it or as much as comes to mind. Um, I was always, I won't say what exactly I was interested in always because um, always is a big word and I didn't learn the word physics essentially until college. Until I was in college, I knew in high school that there was a course called physics, but I didn't have time to take it. I went as far as chemistry, and I liked chemistry. And but what I was always interested in is sort of technical things of how things work. That goes back to my childhood. I was always interested in how things work. So when I finished high school and started college and had to choose a subject, I chose chemical engineering because that's got to have to do with how things work, and chemical because chemistry was the most advanced science course I had taken in high school. I didn't know anything past that or beside that. But that lasted one semester essentially because I physics was a required subject for majors in chemical engineering, so I had to take physics, and the minute I took physics, I fell in love with it. So I, I've really been a physicist ever since.
And you also had an interest in music early on.
Yes, I still do. Uh, uh, but yeah, that was uh, basically independent of the other. I mean, I had an interest in music. I continue to have an interest in music too. For my whole life. But the fact that there might be some connection, some bridging ideas, uh, I didn't know that until I was practically an adult, and then for many years I knew that there was a part of physics that had to do with music, well, with acoustics, and the step further into music was a further specialization of acoustics. Uh, I knew that for many years. I mean, I started knowing that when I took my first elementary physics course, because it would have a lecture or two on touching on that, pitch and resonance of pipes and things like that. Uh, what I took a long time finding out about is that musical acoustics or physics of musical instruments or physics of performance spaces, any of those things that had like you can say one foot in physics and the other in music. I knew that it existed, but I didn't know that it had anything researchable in it still. The impression I had is that everything was known that needed to be known. Maybe I didn't know everything, but there are people, specialists that know everything. There isn't a field for research. And actually I found out that there was a field for research. The physics department at one point decided that that to get brownie points with the dean. I mean, it's always good for a department to have students registered, and so you want to have within reason a course that students would be registering for. So they asked me whether I would teach a course in the physics of music. And I said, sure. And of course, I had to do some studying then. I still didn't immediately venture into research territory. That began with a question asked by a student in my course. He wanted to know why a piano is built with 3 strings to every note. That's not literally true. In the bass, they become fewer. But essentially, if you open the piano, you find a bunch of hammers, and each hammer impinges on 3 strings. So the student wanted to know why that was. And I thought about it for a few seconds. It didn't take me long to realize I didn't know the answer. And I said, I don't know the answer. If you were to be in the same class next year, I could tell you. But of course, you're not going to be here. But I will know in a year. I didn't really think it would take a year to get the answer to that, but the course was given once a year. So then I was, by then, a practicing physicist, experimental physicist, and to some degree theoretical physicist. So I just got to work on the problem the way a physicist would work on the problem. And it turned out that the answer to that question was very, very interesting. I don't know whether you know anything about that. It's not optics, but the fact is that those 3 strings are strongly coupled to each other because they're one end is on the bridge, which is essentially the soundboard, which of course moves, vibrates. Otherwise you couldn't hear a piano. So if you were to set one of the 3 strings into motion, the others would pick up the vibration too. So you really have to consider the 3-string system as a single system coupled together, and so it has, depending on whether you want to include polarization too, there'll be 3 or 6 normal modes of a 3-element oscillator, and those normal modes differ radically in how strongly they radiate. because one of the modes is a completely symmetric mode where the strings go up and down together, or up and down. I always think in terms of a grand piano. Upright, they would go like this. But if they go up and down together, the forces that they individually exert on the soundboard is tripled, and the radiated power is multiplied by 9. Whereas the other normal modes, which are, of course, are orthogonal to that, which means that the sum, the instantaneous sum of the forces that they exert on the soundboard is 0. They are much longer lasting. And to a 0th approximation, you'd say they don't radiate at all. Of course, they radiate some. So what you find then, if you look at the intensity of radiated sound as a function of time, when you hit one hammer, one set of strings, you damp everything else, is that you get a very loud sound which decays very rapidly, followed by a very soft sound that decays very slowly. So, and the brain apparently interprets that as being both loud and sustained, which is sort of the best of both worlds. Because if you don't realize that possibility exists, you can still adjust, the input admittance of the soundboard. You can make it large, and then it will be loud, but short-lived. Or you can weaken make the soundboard stiffer or something, so that the coupling is weaker. Then you'll have a sound that's more sustained but much weaker. But apparently, this was, of course, all discovered by trial and error long before there was theory about it, that the piano sound has the possibility of sounding that is being perceived as quite loud and quite sustained. So this is not a trivial aspect of a musical instrument. It has some parallels with other string instruments, but that's essentially the secret of a piano.
Now, you said you were an experimental physicist, and while you were working on music, was there some relationship you felt to like electromagnetic radiation, or, how did you think about this?
Physics always starts with the unwritten assumption that every phenomenon is related to every other phenomenon. So that, the kind of analogic thinking that physics represents, if you take the word wave, for example, the original meaning of wave is, of course, waves on the ocean. Physicists have extended that to waves on strings, waves in solids or liquids, waves in air, which are not described by the same equations. If you're not careful, you will describe them by completely different equations each. But the physicist, because he's a physicist, it always has his ears perked up for some analogy between different phenomena, which, of course, the analogy would be obvious if the systems were closely related in constitution. But waves today include a huge range of phenomena which at first glance have nothing at all in common. And then, but the physicist has managed to invent something called the wave equation, and all of these phenomena can, to some degree, be described by the same wave equation, or by slight variations of it. But so you get the super abstract concept of a wave, a physicist's wave, with tentacles in various parts of nature. And that's what physics is good at, and that's what physicists are always trying to do. That's not true of engineers. Engineers have their own challenging tasks, but that's not one of them. The fact that car noise, automobile noise, has something in common with quantum waves, for example, couldn't be less interesting to an engineer. Now, of course, there are engineers who are like physics, but so I'm not necessarily saying this about individual human beings who can have wide-ranging interests. But as an engineer, one would not think of equating those two, or even thinking of them as having any similarity whatsoever.
So some of your early experimental work, was it you starting with observations, you're looking at other people's observations? How did you
in the acoustics field,
or because physics in general?
Well, because you know, I have worked in many fields, and in a way, the skeptic could say, I don't really know any field in great depth, but the skeptic would be wrong, because the things that he's thinking of are not the things that interest me. Sure, I don't know that I can't speak in depth about the vibration of the concrete walls, but the physicist's hobby, or you can say compulsion, to find similarities, analogies, let's say. Analogies is a good word. To find analogies among different fields is very, very helpful, because you have a kind of unconscious toolkit where you try to look, well, in many cases you look at the equations that describe a certain phenomenon, but it can be much more abstract than that. Somehow you look for something that you would like to call the essential nature of a phenomenon. Of course, that's begging the question, but that's the way a physicist thinks of it. And he does have a big toolbox. In experimental work and in theoretical work, you can do that. I found out very early, as I looked into this piano vibration, that, oh, by the way, well, people have speculated, you know, on sound of the piano. I think there was actually some observation of amplitude as a function of time that showed that double slope. That, but there was no inkling even of an explanation. And it was done mostly by people who didn't feel the need for that because they weren't great physicists. I mean, that sounds conceited. I don't mean that I'm a great physicist, but you know, I've had some good examples. I've been taught by some good people. So the first thing was to observe the effect. Observe it in a quantitative way. So I built a little gadget which could pick up the vibration of one of the three strings. And it was before digital equipment, before digital equipment completely took over things. So this was still with oscilloscopes and analog things. But the first thing I did is just observe that, yes, that's the way the vibration looked. But I also made my pickup in such a way that it could tell polarization, it could tell the direction, the orientation of the vibration. It could tell a vertical vibration, for example, from a horizontal one. Actually, what it measured is the 2 at 45 degrees, which is easier to do if you want some kind of symmetry in the measurement. But you know, it measured phase as well as amplitude, so that you could then add them and subtract them. And I found that the polarization of the prompt sound was perpendicular to the polarization during the after sound. It went up and down, and then it went. And so that way, the idea of two modes being there then occurred naturally to me, because if somebody had asked me, I mean, everybody knows that any vibrating string has two polarizations, and there are two possible modes. But the concept of dissipation is something that traditional acousticians don't like to talk about, because it complicates the equations. But of course, modern acousticians don't. Well, first of all, the mathematical methods have been developed, so it's not that complicated to do a good job of including the dissipation. So the fact that these were two modes of the string was sort of obvious, but the fact that the two modes of the string decayed at quite different rates, like a factor of 10. So that was then just staring me in the face. And it didn't take long for me to ask myself, what causes dissipation in a vibrating string? And I realized that in most musical instruments, the major source of dissipation in a string mode is non-rigidity of the mounting points. That's far and away bigger than air friction, viscosity of air, or internal friction of the steel. They all contribute to, but by far the major thing is the motion of the endpoints. And in a way that makes sense, because that's the way a string instrument radiates its sound. We know that you don't build a musical instrument without some kind of soundboard, and the string is connected or in contact with the soundboard. So suddenly, I mean, it didn't take very long. Once something like that opens up, I won't say you understand everything at that point, but it sort of spreads. It's not a point. It's more like a drop of ink on a piece of blotting paper. The drop is very small, but almost immediately you have a large area that you now understand, because it's very, if somebody asks you why is the mode of the strings that moves the soundboard more lossy than the one that doesn't, that's very obvious, because the soundboard is the loss of energy, and if it can vibrate without the soundboard, it will live longer. So that developed into a considerable theory that I published in the Journal of the Acoustical Society. And then a year later, Scientific American found out about it, and so they wrote it up. They invite you to write a draft, but they write their own papers. But of course, you see it, because sometimes they have blunders in them. But this main point about the prompt sound and after sound in the piano, which is grounded in the physics, but impinges powerfully on the psychology, on the psychological perceptive things. Yeah, I even had a picture of my piano on the cover of Scientific American.
Oh, that's really excellent. I have a number of old Scientific Americans. I haven't pulled that one up yet, but I'll look at that.
Mm-hmm.
But I did see your later papers where you worked with violin and,
Yes,
and other
yes.
things. Now, at about the same time, you were also began to work with quartz crystals, or was this just before you started to work with crystals?
It was after the crystals. You're talking about the connection with nonlinear optics, turned into the connection of nonlinear optics. It was my first year at Michigan. And so one of the things, before I was at Michigan, I spent 7 years at Bell Telephone Labs, which was still a powerful idea factory at the time. And before that, I did a dissertation on atomic beam spectroscopy, on the structure of the metastable state of helium. When I was at Bell Labs, I was in solid state, which was new to me. But I've loved that all my life. Learn something new, and one of the things, As a matter of fact, acoustics was marginally involved at one point because there's something called the acousto-electric effect. It's not, the name is not mine. Acousto-electric effect describes the phenomenon that takes place in some solids, that if you propagate an acoustic wave, you know, a solid acoustic wave, through it, and if it has to be a conductor, in fact, it has to be a semiconductor, it turns out, it will sweep electrons along with it, so a current will result if it's short-circuited, or a voltage if it's open-circuited. And the man who thought of that and wrote a theoretical paper that was published in Physical Review, which is how I got to it. I saw the paper in Physical Review. It didn't take me long to understand that the paper was just absolutely wrong. It started out from a place you can't get there from here. It just doesn't work. Primarily, he had forgotten about the fact, I mean, the model one has in mind, the picture one has in mind is of an ocean wave which coming into shore will carry all sorts of debris with it. So if you now transpose the ocean wave into an acoustic wave and the debris into electrons, and postulates that there's an interaction between the electrons and the straining of the lattice, so that, for example, they prefer a compressed lattice, or the other way around. That just as the ocean wave carries the debris, this wave will carry the electrons. So it's a clever idea. The only thing that's wrong with it is that it's wrong, because the major force on electrons in a conductor that try to bunch is space charge. The electrons repel each other. There's a strong energetic desire for a uniform distribution of electrons. And when you put numbers into that, it turns out that it's many, many orders of magnitude larger than the acoustic forces. So, in fact, you don't see an acousto-electric effect by putting sound through a metal. But then my thinking, because it was such a pretty idea, I started to wonder, would it be possible otherwise, if it, or in some kind of situation? And there are a lot of semiconductors, including germanium and silicon. They're called many valley semiconductors. Does that mean anything to you?
To me personally?
Yeah, no, yeah. Well, it has to do with the diagrams, with the energy levels of an electron in the lattice, without any compression now. The lattice is given, a fixed lattice. What are the eigenstates of electrons in that? And one sort of assumes that if the propagation vector is zero of an electron at rest, by symmetry it will be either at the maximum or at the minimum of energy. And if there are very few electrons, it'll probably be a minimum. But the fact is that these many valley semiconductors, their energy diagram, energy level diagram, it turns out that the center of what's called the Brillouin zone, I don't know whether that means anything to you. It's the graph of energy levels as a function of what's the propagation vector of the electron in the lattice. The center is a maximum, so there are no electrons sitting there in the semiconductor, but the minima, because they have to have the symmetry of the lattice, there are 4 of them. They're symmetrically located, and their response to a compression is that the energy goes up for 2 of them and down for the other 2, which means that the kind of bunching that an acoustic wave would cause will be devoid of space charge, because there are 4 types of electrons. They all have the same charge. They're electrons. But their response to the acoustic field is opposite. There are 4 classes, and 2 of them go up and 2 of them go down. So they don't build up any space charge. So I started working with that idea, and I was able to sketch out the theory and then do the experiment and observe it. So when I came to Michigan, one possibility that's chosen by many new professors is, I mean, if they're not straight out of college, straight out of graduate school, even if they're straight out of a graduate school, they'll have done a doctorate and have a specialization, because they're specialists in the subject of the doctorate. So the majority of young professors will do research that ties up with their thesis subject. So that's one thing I could have chosen, is to continue work on the acousto-electric effect. And in fact, I did that. I had 2 graduate students, 3 actually, 3 graduate students who I'm not sure now whether it's 2 or 3, but it doesn't matter. I had a few graduate students that whom I just gave problems of continuing to investigate the acousto-electric effect. What happens if you do this? What happens if you do that? And you know, it was good physics. But I started at the University of Michigan in the winter semester of 1961. My friend from graduate school, Peter Franken, was my colleague from graduate school. He had just come up with the idea of optical harmonics. And I had nothing to do. I was not much invested in anything. So I joined that group. It was a group of 4 people. The paper, I think paper gave the authors in alphabetical order, so it was Franken, Hill, Peters, and Weinreich. Was the original observation of optical harmonics. The order was alphabetical. I mean, that's common in physics groups where people are not particularly cutthroat about having the glory. Is instead of trying to think who contributed what percentage to the success of this project, you just say alphabetical order. Leaves me at a disadvantage because I'm always last in the alphabet, but also it never bothers me because, you know, it's not the last. No physics paper that I've published was the last word on the subject. In many cases, it was the first word on the subject. So in any case, Bill Ford, excuse me.
Oh, so Franken had the idea for the experiment.
Right.
Okay. Did he have any lab equipment to do it with, or
no? But he had a lot of lab equipment. He was doing optical spectroscopy, but nothing. He had to generate that. He was a very good operator, as they say. He knew people. He could borrow stuff from people. And Bill Ford, who was also in the department at the time and was not part of the experiment, but he explained, had this bon mot that which he characterized the way the experiment worked. Franken had the idea. Weinreich understood the idea. Peters knew how to do it, and Hill did it. So the way I remember it is that Peter came to me. I mean, you know, we had offices not that far apart from each other. He came in. He had been to an optical society meeting, which he said was very boring. And so he had time to think about physics instead of thinking about what the speaker is saying, which wasn't interesting. And then he had this idea that electromagnetic theory is a linear theory. And probably in a vacuum it is linear, although with quantum electrodynamics that's not true either anymore, but that's much, much higher frequencies. But Maxwell's equations are linear. But in a medium where let's see, how did it? Yeah, in a medium where, the electromagnetics, it's not the nonlinearity of the medium mechanically, which is also there. It has elastic limits and breakage points. But that's not the one that was involved here. It's the nonlinearity of the material electrodynamics, which is, for example, the dielectric constant, which comes about because of the polarizability of a lattice, that when you put an electric field in it, the force is equal and opposite on the charges, on the ionic charges. And so there's a displacement of polarization generated. But that can't be linear. I mean, it depends on distorting the lattice, and you know, obviously, if you distort it by an amount that's comparable to the lattice constant, it won't be linear. It'll crack probably. So we don't know where the nonlinearity would start, but let's find out. The way to find it out is to put a huge intensity optical pulse into a dielectric medium. And look for second harmonic generation, which is what you get when you have nonlinearity. So he told me about this. He was tacitly inviting me to join the project, which I was glad to do because I was never, I was always tend to be a multi-project person. I was involved in many things. But he proposed, and lasers were fairly new at the time. He proposed taking the most powerful laser that would then be available and focusing its light focusing its light on a piece of glass, which is just something that's transparent material. And then look for blue light in the output. Obviously not an easy experiment because the blue light isn't going to be strong, and there's any detector of light is in danger of being swamped by the huge amount of red light. But when he told me this and said a piece of glass, I said, "You mean a piece of quartz?" Because I had been dealing with crystals, and I could see that the symmetry of glass is such that there won't be any second harmonic. There might be third harmonic, but that's another few orders of magnitude harder. But quartz doesn't have a center of inversion, so second harmonic generation is not prohibited. Let's look for it. So that's what Bill Ford meant when he said Weinreich understood it. Of course, I didn't understand it. That was the beginning of understanding, but I had no idea, neither did any of us have any idea of how one would go about calculating how big that third harmonic coefficient, whatever way you define it, how much you can expect in the way of third harmonic. And if you really don't know how to calculate it, it's not a bad idea to try the experiment anyway. You don't insist on understanding it before doing the experiment, but it would be nice. But we didn't do that. And it turned out that whereas the logic of choosing quartz over glass was foolproof, quantitatively it was utter nonsense. I mean, it's true you had to have something with lack of center of inversion. I just said, he said glass, I said quartz. But in fact, when you start making the theory of second harmonic generation, it's always the electrons in the medium rather than the ions, the electrons being virtually excited. If the electrons have a nearby state that has opposite parity, that will give a big effect, because the coupling of the two can happen relatively easily because they're almost at the same energy, and they will split into states which are not parity eigenstates, but one points this way, that they're like vector eigenstates. So that would, and so that all became clear, not to us. I would think that given enough time, we would have thought of it too. But of course, one rule that was very strongly self-enforced in the precincts that I came from, and with regard to physics, was you don't keep secrets. So with something like this, just the idea got huge circulation because we wanted it that way. There wasn't a paper published, but there was just word of mouth. And other people thought of that. And that's how barium titanate got into the picture. That was an generally ferroelectric things are likely candidates because the ferroelectric state is already a state. The material might have the essential material might have inversion symmetry, but the state is a split state and does not have inversion symmetry. But the ferroelectric transition is not a very high temperature transition, so it's not a huge energy difference. So that's ideal. The other crystals have since been used, but that was the original logic of how barium titanate got in. And with barium titanate, you could see the blue light. I mean, with a spectrometer, you could see the blue light. And in due time, I don't remember what other techniques had to be perfected for that, but they were. It was actually possible to put a red beam into a medium and have a blue beam come out. The red beam was completely extinguished by second harmonic generation. Lots of things had to be understood before that happened, like phase matching. Also not our idea. In fact, I remember giving a colloquium in those early days on why it would be impossible to have a finite transfer of energy, but it would always be in space a fluctuating transfer of energy. I didn't think of the fact that it's possible to choose a direction in which the extraordinary red beam has the same phase velocity as the ordinary blue beam. And so they just gobble each other up until there's nothing left. Of course, the phase difference is now the opposite, so it comes back. And those beautiful experiments were just post-dated us.
So having the right crystal was really essential to detecting a signal.
Well, we did detect the signal. There was this famous story of the dot in the figure in the Physical Review Letters figure. We worked very hard to have the spectrometer, set up in such a way as to maximize the possibility of seeing anything. And the plate that was taken, the spectrographic plate, had a huge halation at the spot where red light came, and tiny black pin mark where the blue light was. But you know, we looked at that a number of times and did careful measurements and whether it was really the same dot all the time and whether it was precisely at twice the frequency. And it was. So we published that in Physical Review Letters. But the figure person, not a physicist, who gets these drawings all the time and has to clean them up before he makes the cut to print it, thought that was a fly speck. And so it was published. And it's still a standing joke. But the interesting thing to me, also, something that I'm proud of, I mean, not I personally, but the culture in which we had learned to do physics from our masters, from our professors. We never published a retraction or a correction and an erratum, because any fool would understand that we would not have published a picture like that with an arrow pointing to something that isn't there. I mean, that would be crazy. So since we were fundamentally physicists who could be trusted, and that's what I'm proud of, could be trusted not to cheat, not to make it look as though that's what happened in order to be able to claim credit where credit wasn't due. It was clear that we didn't do that, and so there must have been a point there. So it was a standing joke, and orally, of course, we took part in lots of funny discussions of that. But it was never put into print because it didn't need to be put into print. It was part of the physics culture that things like that, you know, and I've thought about that many times. It's the only time, well, it's not the only time I've been in that kind of situation. There are times when I actually published something that was wrong, an experimental result that was wrong, because I hadn't thought of something. And then, of course, I did publish an erratum. But, you know, in physics, your project is never finished. Your project is just never finished. You may leave it for something else, but it's never completely done. And the horizon is always equally far. So if you look ahead, you will not sense the distance that you have come. What you have to do is look back, and then you can see the distance that you've come. But the work is never finished, and that's different with an engineer. I mean, you know, it's not black and white different, but an engineer has a task which has an ending. There's a task that he has undertaken to do, and when that task is done, his work is done. That's not true of a physicist.
So pretty fascinating. So you published. You had an arrow pointing to empty space. And you knew this was a pretty significant experimental evidence of nonlinearity in optics. And then And then you continued your work with spectroscopy, and as I understand it,
Actually, I stopped at about that point and went over to yet another field. I didn't, you know, I'm not good uh, at see, how shall I put it? When there's an implied race, and you know, with the number of people who at that point got interested in nonlinear optics, every place at Bell Labs, MIT, you know, Harvard, all the big guns of physics were in that. Uh, I don't work well when I have to watch the time. And after all, it would have been different if I felt that I had some kind of ability that was so exceptional that they just won't find a solution unless I'm part of the team. But you know, I never felt that. I thought of myself as a pretty good physicist, but my style of working isn't that. So that was a good time for me to get out instead of having others breathing down my neck, because it does make a difference. You don't continually want to be second or third. I mean, you feel like your time is wasted because human knowledge wasn't advanced by your effort. People already knew it, and you came in 10 minutes later, but the race had already been won. So that's not constructive. My forte generally in style is to look for something that, as it turns out, I'm the only one who has thought about it, and I don't need to keep a secret because I've thought about it so much that nobody I know, it can happen. No, but I'm pretty sure nobody is going to catch up with me like with the piano business. There's nobody working in that. There was nobody working in that field who can work better and or more thoroughly than I, because of the field, because of the nature of the field. I've had physics as part of my nature, and generally combining physics fields is something I like to do. It could have happened. I mean, it has happened in some cases. I don't fool myself that in no case did I do something in musical acoustics that nobody else had done before. But in a number of cases, I think I have been the opener of a field.
And that's one of in the Optical Society, we were thinking informally about trying to commemorate some of these events and maybe give a sense of the history or the way of thinking or the motivation or something. Maybe it's inspirational or illustrative of some process of science. So, not to go away from some of your work, but are there some other events that come to mind that you think would be significant for us to put on agenda to think about? I mean, there's, you know, the optical fibers,
Mhm.
there's side-looking radar. You were probably close to that group. I'm thinking you were in the, were you in the Randall lab at this time?
Yes. But I was not in the radiation laboratory. That was one floor up. So that those. Well, I mean, some of my fellow students were there, and the faculty that I was taking courses from, some were working in that lab, but I wasn't involved. So the radar kind of the radar developments I had nothing to do with.
Okay.
Well, just the maser thing altogether, just the idea. Uh, that's characteristic of what I would think of. I mean, not the idea, but the way I think of those things is it's the same thing. It's a continuation of the same thing. It started out with towns wondering about whether stimulated emission could be made coherent.